Time series forecasting task with recurrent neural networks, LSTM, forecasting stock price prediction using machine learning. Have you ever wondered if networks can actually retain information? Well, recurrent neural networks, RNNs, do precisely that. Specifically, we'll be utilizing long short-term memory, LSTM, networks, a subset of RNNs, to analyze sequential stock price data. By leveraging past values, we aim to predict future trends. Contrary to magic, predicting the future is a skill you can acquire too. Recurrent neural network. Recurrent neural networks, RNNs, store and reuse output activations from previous layers when processing new input, incorporating past information into predictions. However, RNNs face the vanishing gradient problem, limiting their ability to retain long-term information. The vanishing gradient problem occurs when gradients become very small, hindering effective training. This is exacerbated by traditional activation functions like hyperbolic tangent, causing gradients to shrink exponentially with additional layers. Long short-term memory. Long short-term memory networks, a type of RNN, address the vanishing gradient problem. Unlike traditional RNNs, LSTMs retain long-term information over extended data sequences, making them effective for time series tasks. LSTM Architecture. The architecture of an LSTM network consists of LSTM units, also referred to as blocks, which serve as the building blocks for the network's layers. Each LSTM unit comprises a cell, along with input, output, and forget gates. The cell is responsible for remembering values over arbitrary time intervals, providing the network with the ability to retain information for long periods. Meanwhile, the gates regulate the flow of information through the network, controlling the input, output, and retention of information in the cell. How LSTM work. LSTMs work by processing input data sequentially, with each LSTM unit receiving input from the previous time step and generating output for the current time step. The cell's memory state is updated based on the input data and the current state of the gates, allowing the network to learn complex patterns and dependencies in the data. Additionally, LSTMs are trained using backpropagation through time, BPTT, a variant of the backpropagation algorithm that accounts for the sequential nature of the data. The dataset represents the trend of Amazon stock from 2006 to 2018 and is available on Kaggle. Here is a description of the features. Date, in the format EMDD. Open, the price of the stock at market open in USD. High, the highest price reached during the day. Low, the lowest price reached during the day. Close, the closing price of the stock. Volume, the number of shares traded. Name, the stock's ticker name. The dataset consists of 3019 data points, each representing one day of the stock market for Amazon. Visualization of the data is crucial for analysis. Let's create a single trend line chart to plot the stock price of Amazon, AMZN. Over time, for our model building, we will focus solely on the close feature of the dataset. We'll scale its values to the range, 0,1, to ensure computational stability. To prepare for predicting future values, we'll split our dataset using the year 2016 as the split point. Data from before 2016 will be used for training, while data from 2016 onwards will be used for testing. We will now construct the basic data structures that will be fed into our model. The input for our model will be sequences of closing prices spanning 60 days. The output for our model will be predictions for the closing price of the next day. Here, the window size of 60 is a hyperparameter, and changing it will affect the network. Essentially, based on the past 60 days, we aim to predict the closing price for the next day. Modeling. We can now proceed to build our model. Using Keras, this task becomes straightforward as it provides pre-built RNN layers. We'll stack a few LSTM layers followed by a few dense layers for the final prediction. Once our model is constructed, we compile and train it. We'll use the atom optimizer and mean squared error, MSE, as the loss function, given that we are predicting a numerical value. Training the model for just one epoch should suffice. However, please note that LSTM models can be computationally expensive, so this process may take some time depending on your hardware. Inference. With our model trained, we're now ready to make predictions for future stock prices. We'll pre-process the test data in the same manner as we did for the training data to ensure consistency. Finally, let's create a single plot that displays the training data, the test data, and the predictions. As depicted in the graph, the predictions closely align with the actual values, test data. This is fantastic.